Hi, we are going to see on FEKO, I'm showing here the model, how to design a simple Wilkinson power divider. I'm showing here the picture of the Wikipedia. As you can see here, the Wilkinson power divider from Wikipedia, we can see that it's a three-part structure, is a planar structure from the picture. We have actually these transmission lines. They are 90 degrees here and here. And if you take into account that the reference impedance to be 50 ohm as usual in microwave and RF, this resistor here is supposed to be 100 ohms. And these two lines here and here, they are supposed to be square root of 2 times 50, which is more or less 70 ohms. What's the purpose of this Wilkinson power divider? Actually, we have to divide the power from P1 in half to P2 and the other half to P3. It sounds very simple if you think in terms of low frequency, just divide a signal by 2. It's just having 2 wires. You don't need to have all this difficult, complicated structure. But if you think in terms of a higher frequency, things are a little bit more complicated. Why? Because it's not enough to make sure that we have half power here and half power here. We have to be sure first that all the ports are matched. So if I am sticking if I'm sticking a generator here, I have to be sure that there is no reflections, so the energy bounces back from the structure. And also, and this is more complicated, it's not very easy to see, we have to be sure that there is no communication between these two output ports. What I mean is, imagine that you have a generator here, and you have 2 antennas here, one antenna here and one antenna here. I have to be sure that there is no communication between the antenna over here with the antenna over here. That means that the coupling between these two parts should be as high as possible. So this part here doesn't feel what happens here. So even if I short circuit P2, P3 should be working, in a normal way. And that's the beauty of microwave and RF. I can get this working in a passive and a simple structure with all this isolation, with all this matched ports, because I have this 90 degrees transmission lines here and the resistor. That's the difference between high frequency and low frequency. The phase information makes possible this structure here with the isolation with the matching at all these 3 parts simultaneously. So going back to our model in FEKO here, we can see that we have the same drawing from the Wikipedia, something similar here. This thin microstrip line, it has this length, and it's supposed to be 70.5 ohms. And these 3 guys here, they are supposed to be the 50 ohm lines to be connected to the connectors, SMA or N connectors, whatever. And as you can see here, the structure is floating on air. I made it so that the simulation runs faster in FEKO. I have assigned, just for the sake of simplicity, to make it a very short simulation, I have set 50 ohm reference impedance, as we said, as usual, 5 gigahertz. And first thing we need to do, we need to find a way to design what is the width of all these transmission lines here. So we have several applications. For instance, this one here, this is emtalk.com. We can have a microstrip line calculator here. As you can see here, I typed in the dielectric constant to be 1, which is air. styrofoam, for instance, if you want to build this structure later. And I have set the height of the dielectric to be 1 millimeter and the frequency of 5 gigahertz. So first thing here, as you can see, I try to find what is the width that corresponds to the impedance of 70.5 ohms. And I click here in synthesize, it's already done, and it's 2.95 millimeters. And also I need to see, as you can see here in this drawing, in this picture, it has to be 90 degrees, or it means a wavelength over 4, 90 degrees, at a frequency of 5 gigahertz. And as you can see here, it corresponds to 15 millimeters. And I also need what is the length, what is the width for 50 ohm. I type here 50, synthesize, and I see that the W for 50 ohm is 4.91. Before we start, we have to analyze this structure here. There is just a small computation to be done. As you can see here, this is the length of this transmission line is supposed to be, in our case, 15 millimeters, right? To be lambda over 4, it has to be 15 millimeters. So in order to build it in FEKO, just coming back here, this is the structure. This is called elliptic arc. This is the primitive that FEKO uses to construct this piece of transmission line. So as you can see here, we have to inform what is the radius of this structure. In other words, we have to compute what is the radius of a 90 degree, which is a quarter of a circle, a circumference. What is the radius that corresponds to a length of 15 millimeters? So pi times 2 times the radius is equals to the length of a complete circumference. If you divide over 4, get it for just a quarter of a circle, we have the radius, which is, in our case, making the computation, I did already, 9.54 millimeters. Right? It corresponds to 9.54 millimeters. That's the radius that we need to use to get the total length of 15 millimeters. You can check later the computation. So just to make sure that you understood, it's just a very small step before we start drawing and designing the model. So we start with the FEKO in the blank session. First thing we design is this elliptic arc. We find it in construct, elliptic arc. And here we place the radius. As you computed the radius before, it's 9.54 millimeters. And here we type in 90 degrees. As you can see, don't see anything. Here is this, the length of this, a quarter of a circumference. This is just a curve, a 2D structure. We need to make it a trace, a transmission line. For that, you just go to work planes and you select right click, add work plane. And instead of typing in which numbers, which coordinates you need to choose from, you just Ctrl and Shift and just select this point here. You type in create, and it's very important you go back to work plane 1 and right click, set as default. Now you can see it, and now we have to design a transmission line, a line here, whose length is, going back to our calculator, 2.95. We need to make it half to each side. 2.95 times minus 3 minus, here is 0, and I have just to get rid of this minus here and create. Then we have this transmission line. And once you created this line, you just go to path sweep, you select the curve. It's ugly right now, just type in create, and that results in your transmission line. Just going back here, 2.95, 2.95 over 2, just 75, that's fine. Yeah, that's all right. Once you have done half of this transmission line, we just need to make it mirror to the other side. We select this path sweep and we go copy and mirror. You see what happens? It just shows the ghost image. In case you don't see it, you just need to go to this work plane area here and type in all the different options till you see something like that. You just type in OK, and now we have both transmission lines. Well, we have almost everything done. We need to make these pieces of 50 ohm here. Just refreshing our memory, instead of 70.5, we type in 50, and it's 4.9. 4.9. It doesn't matter the 50 ohm which length you use for that. It doesn't matter. So we go back here and we come here to construct rectangle. The rectangle is supposed to be built like that. No, it has to be shifted. We go here, here, there we go. And then under geometry, we just select this option here. Don't worry about the position, the overlap. We are going to fix it soon. So as you can see here, just paying attention, the width is supposed to be along the U coordinate. This U coordinate, it's supposed to be this thing here, this direction over here. This direction over here is 4.9. So we just type here under the W, 4.9 minus 3 millimeters. And here, the depth, let's write it, for instance, 5 millimeters. Something like that. You see it's overlapping. And then I can use this trick, transform. You see it's selected here. Transform, translate. In order to translate it, I just type in Ctrl-Shift from this middle point here to this middle point here. Okay, there we go. So this is very thick transmission line because we are 1 millimeter from the ground plane. Just checking in if you want to see if the width is okay. We just type in this tool here. Ctrl-Shift from here to here is 4.9. That's fine. And again, let's measure it here. From here to here is 295. That's fine. And then we just need to copy this piece of transmission line from here to here. We go copy and translate. Ctrl-Shift from here to here. Okay. Again, copy. I have to type in here. Copy and translate from here to here. Always pressing Ctrl-Shift. Now we have the 50 ohm lines here and the 70.5. You see that I left these two transmission lines, they are overlapping. You could make a better design. I'm just doing for the sake of make a very quick modeling, but you can make it much better later. And now we need to design the ground plane. As I said, we don't need to worry about the substrate because it's considered to be air. FEKO doesn't care about it. Now we need to design the ground plane. So in order to design the ground plane, a very simple way to do it without having computations and making finding numbers, etc. We just align the working plane here in this corner. So work planes, right click, add work plane, Ctrl-Shift here, create. We go to this point here, we just created, set as default. And now we can design our rectangle. you can see that the V, it's over here, and it corresponds to V is over here to the D. So we just go, this is the base corner, it's the 0, it's the origin. The W, it's from here to here. It's supposed to be here. And the other point is supposed to be here. You have to see something like that. Great. You see? There you have your ground plane. The ground plane is on the same plane of our structure. So what we do, we just select this rectangle, transform, translate, and we go from 0 to 1 millimeter here, minus, it has to go under, you see? And now we have to excite this structure. There are many ways to do it in FEKO. There are other videos showing this source and load, edge port, etc. Let's make it very simple. We are going to use this wire port, and now we select here line. We go Control Shift from here to Control Shift here. Great. One line is done. We shift it with the mouse, line again, Control Shift here, Control Shift. And now you see the problem. I don't see any point to pick here. A trick that you can use is I select here in yellow the same point, but here I know it's 1 millimeter down. I just type in same 1 millimeter. I do the same for the other part. Line, I type in here. In the yellow here, I type the same. But here I go to minus 1 millimeter. And then we have to think about our resistor. How can we model a resistor, a 100 ohm resistor here? Very easy to do, a way to do it on FEKO. We do a line here again, Control Shift, for instance, from here to Control Shift here. Design another line, and now we assign these lines to ports. We select this line here, wire 14, right click, create port, wire port. Create. It doesn't matter if it's here or in the middle. It shouldn't make any difference. We select the other line here, 15. Right click, create port, wire port. Create. We rotate it. Now line 3, wire 16. Right click, wire port. And finally, the last wire that you just created is line 4. We select line 4, wire 17, create port, just to make it a little bit more consistent. Just for this case, we select middle. Now we are done. And we have to tell that this wire here corresponds to what? Source load, add load, port number 4, a resistance of 100 ohms. Create. I guess everything is more or less done. We have to inform the frequency. Let's type in from 3 gigahertz to 6 gigahertz, 51 points. Should be quick, depending on the computer. And now we have to request, this is very important, the multi-port as parameter. Port number 1 is 50 ohm. Port number 2 is 50 ohm. 1, 2, and 3. All of them are 50 ohm. What about port number 4? Port number 4 is not supposed to be excited. You can see this as the ports you should be connecting to a network analyzer. That's more or less the meaning of setting all these ports here. Add, close, just checking in if everything is all right. And we can take a look at the mesh. It's supposed to, is asking the wire radius. Let's put it 1/10 of a millimeter. All right, you see it's a very coarse mesh because our structure is small. And now we can, oh, I just forgot something very important. We have to select all the structures that we just created, including the lines, and construct union. Because we need to tell FEKO that all these structures, they are electrically connected, right? And we can see the mesh again, right? And now we can type in FEKO solver, and it's running. Okay, 100 here, 100 here, I type in OK, and I can go to post FEKO, and it opens up the model, the 3D model here, as you can see. I go to Cartesian, and I just drag and drop the S parameter. This is showing the S11. As you can see here, I choose dB. So you see the reflection loss of the port number 1 is very low. I can add all the other curves. So I go to trace, duplicate trace, type in here. Instead of 1,1, I choose S22. You see, S22 is not as good as the port number 1, and it's very likely that port number 3 is the same because of the symmetry. There is a very slight difference here. It's cool because it's still below 10 dB. This is probably because we have the ground plane finishing exactly on the same level, on the same height of the transmission line. The transmission line doesn't like it. The microstrip line doesn't like it. So that's one of the possible reasons of this result. And finally, we need to see if we have 3 dB from this part to this part. Let's come here, duplicate trace. We select here, and this is supposed to be 1, 2. And as you can see, this blue here is the transmission. I can go to measure. I can go here to measure cursors, and you can see here is 3 dB, half power. S12, I can go to duplicate trace and see 1, 3. Duplicate trace. Oops, wrong here. Wrong here. It's a trace, duplicate trace. I can pick 1, 3. And as expected is the same as 1, 2. So we have half power. We have 1 watt here, half watt here, half watt here. And it's quite bandwidth, broad bandwidth, as you can see, from 3 to 6, it's working more or less fine. It's below 10 dB. And what is very important, as we said before, we have to make sure that there's no communication between these two parts here, right? So in order to check if it's working, we need to see the S parameter S23. We come here. We select this, duplicate trace, and this one here, this one we pick S23. As you can see here, S23, I'm going to make all the other ones invisible, just for the sake of better understanding. We have a 6 dB of isolation. This is not good. This is absolutely a very poor result. We should work on this structure to make this isolation increase. As I said, one of the things we should investigate is making this ground plane larger in this direction here. This is one thing. The second thing, we could, one of the possible reasons for that, this connection between just going to display turning off the overlay. Probably this connection here of the resistor, 100 ohm resistor, is too long. It's probably creating some inductance or parasitics on this structure, so we should work on the layout to make this connection not as electrically long as it is right now. That should be another option to improve our design. So that's it. Basically, we can design a Wilkinson power divider very simple, very fast and very quick, and analyze it inside FEKO, taking into account the parameters, the S parameters. Thank you very much.